So this is the third part of the series of lectures, and today we will concentrate on arithmetic part. But before doing so, I will have to tying up some loose ends. From the last lecture, where I explained the origin of the n-integrality of holomorphic periods, of the theorem of Cristol, and as formulated in the book by André. And I explained it for the curve case, and then said in the other case it just generalized. But that statement, whatever truth is in it, hides some important technical aspect which I will like to mention nevertheless. So it is a rather deep consequence of Hodge theory. So, and this is what I totally suppressed in the last talk. So let's briefly go through that. So we have the notion of Hodge structure. We will be a Q vector space infiltration, and the complexification of that vector space is given the structure of a direct sum decomposition in complex subspaces, complex conjugate E plus Q equals N.
The C and Q first.
Oh, this Q C of weight equal to N. So the N appears here, and so the Hodge filtration is equivalent datum to this direct sum decomposition. It is an increasing or decreasing filtration, -1 H. So the Hodge filtration is obtained by taking this Hodge group and then this one plus the next. This gives a filtration, and using the complex conjugation and the filtration, you will be able to find this decomposition. This is the notion of Hodge structure. Then there is also the notion of a mixed Hodge structure. So these are pure linear algebra objects. So it is a Q vector space with two filtrations. And this filtration here is a increasing filtration, and with the property that if you take the graded parts of the weight filtration, so that's the quotient WK modulo WK minus 1, on that there is an induced filtration by F, and then you want that this, let's put it this way, is a Hodge structure of weight equal to K. And these linear algebra objects you find a lot in algebraic geometry. The structure of the cohomology of a variety, or a Kähler variety, a smooth projective or a smooth Kähler variety, has naturally attached to it such a Hodge structure. And every quasi-projective variety with singularities or not, it need not be closed, or can be has a natural filtration like this with this property. This was the discovery of the lean. The development of mixed Hodge structure. So any variety appearing in algebraic geometry has a natural mixed Hodge structure. And the singularities determine this weight filtration, or the way you can compactify it influences this weight filtration. The inspiration for the fact that there is such a filtration came actually from arithmetic, so we will come to that. And the last notion, which is used in that proof, is the notion of a special mixed Hodge structure, which is called a limit mixed Hodge structure. So there are the mixed Hodge structure and Hodge. Limit mixed Hodge structure is a special type of mixed Hodge structure, which appears in the geometrical case when you analyze degenerations of varieties. If you have a family of varieties, maybe a family of elliptic curves or a family of higher dimensional varieties, then one can draw this diagram and look at a family of varieties which for t equals 0 degenerates in a singular variety. And usually, so it might be over any one-dimensional base, but one can restrict to a small disk. So imagine that xt is a family of smooth projective varieties. T. Then in the limit, it goes to some singular variety. And now attached to this situation, you have the mixed Hodge structure of this singular fiber, but there is something coming from the way this variety collapses to this variety, and that is a limit mixed Hodge structure. And for that one makes what is called semi-stable reduction. So you may replace the parameter by a power and may blow up and make blow downs, and then you get to a situation where you have a new family you have a new family where now the D, this is what formerly was the x0, so you change the singular fiber so that it becomes a reduced normal crossing. Divisor. First you make a base change, t goes to a power of t, and then you get what is called a semi-stable, you can get a semi-stable reduction. So this is already a difficult theorem. And in this situation, the monodromy transformation has become unipotent. So in general, it was quasi-unipotent. A power is unipotent, but by doing this base change, you make the monodromy becomes unipotent. And you can take the matrix N is the logarithm of that unipotent matrix. So this T is a, you maybe can do it like this, and then you expand this in a logarithm in a series. But T is a unipotent matrix, so T minus identity is a nilpotent matrix, so this is really a finite series. And this is called the monodromy logarithm. And this monodromy logarithm is used to define weight filtration, monodromy weight filtration. The unique filtration on with the property that it shifts the weight by 2, and it sets up an isomorphism of the graded pieces n to the power. Okay. So if you imagine you have a vector space with a nilpotent endomorphism, there is a unique filtration with these properties. The way how you do it is any nilpotent matrix has a Jordan decomposition. You look at each of the Jordan blocks, and you now, in these vector spaces, you have form strings, vectors, which gets mapped to 0. So if you have a vector 1 cross 1 Jordan block, then which is immediately killed by n, then I make a here, and if you have a 2 cross 2 block, you get 2 vectors. This gets mapped to 0. It gets mapped to 0. So there is 2 vectors. The image of the first vector is the second vector, and that vector is killed by the by n. And so here is n is acting. And if you have a Jordan block of size 3, and then there are a triple of vectors which form such a string. And now the weight filtration is just taking these layers. This defines a unique filtration on your vector space. I didn't say what the underlying vector space is. In this case, it is H. Yes? -2. So it decreases so these blocks which are of size 1, you put them in weight n, and this is becoming in weight n plus 1, and this is in n minus 1, and so you order your basis vectors according to this nilpotent. So this is a linear algebra exercise in linear algebra 1, but it is never put because it would be no motivation why you look at this filtration. So what one does is take sort of the limit of t goes to 0 of the homology of this fiber. The homology of this fiber depends on t. For different values of t over a disk, these groups can be identified because it's a topological thing. Same you have with the Hodge filtration. So we will let lim So this is more subtle. Here you have the Hodge filtration is a filtration by subspaces, and it's not obvious at all that if you go with your t to 0, that these subspaces tend to a certain limit. But they do, and then this defines a filtration on the limit. And now the limit mixed Hodge structure is this space, F lim, and this monodromy wave filtration. The limiting mixed Hodge structure. So in any case where you have a degeneration, you also have this special mixed Hodge structure. Now the crucial statement that is used in the proof of the theorem is that follows from Steenbrink's work, because Steenbrink gives a description of these objects in terms of the divisor D and the way they intersect. Say that lim is non-zero. So this is if you have the condition that you have a maximal Jordan block. This happens exactly. There exists a point in the divisor where the plus 1. So the dimension of my variety is n. The di are the irreducible components. So d is the union of di, irreducible components. So for a curve, you have two divisors which intersect, and then we went to that point and we analyzed around that point. For a family of surfaces, you get three divisors which intersect, and there is a vanishing torus. There is a vanishing circle, vanishing torus. This repeats in all for every dimension. But the fact that there is such a point necessarily that these divisors have to intersect. We must remember this is a very non-unique thing. There are many different such semi-stable reductions, and it depends on many choices. But whatever you do, the combinatorial structure of these divisors is fixed. And in fact, you can make a much more precise statement that the whole combinatorial structure of the divisors is reflected in the weight filtration. This fact is the fact you use here for the proof. So this is what I wanted to add, and this is so this is the work of Schmidt, and Steenbrink spelled it out in the geometrical case, and it has strong geometrical applications. So now I want to start the topic of today's lecture, and it will be about point counting. Counting points of varieties over Fp. If you have a variety, say, defined by polynomials over a finite field, and so this would be X would be a affine variety, also is 0. So you equate to 0 a certain set of polynomials, you get a subspace in the affine space. It would be an affine variety. If you take homogeneous polynomials, you get a subvariety in the projective space. But now Fp is a very small field, and you may look at extension fields or any overfield, and then you can talk about the points of your variety lying in that field K. That is just the tuples x1, xn in that, such that if you substitute in these equations, 0. So you look at the solutions to these equations in, well, maybe FP, but also all extension fields, and you get x FP. So these are the solutions to the equations with coordinates in FP. You can look at the solutions with coordinates in FP squared, and so you get a whole set of sets, chain of sets, and but these are all finite sets. So you count this is a finite set if K is a finite field. So you get numbers. NR is NR of X, which is just defined to be the number of elements of that set. It's the number of points of your variety in that extension field. The field with p to the power. There's all variables. There is something in mathematics that you always run out of letters. And this happens always. You get a certain...
Double notation is allowed.
Yeah, it was clear. But asking is also always allowed. Yeah. You get in devil's kitchen, yes. So, and then you can form the congruence. So if you're given an equation x, it's far from simple to determine these numbers, although you might use a computer program to compute a few of these numbers by just substituting, looking if the equation is fulfilled. One of the great insights in the modern era is that there are very quick ways of determining these numbers, and that they have remarkable properties. So, but even if it is a very good exercise to determine this for, say, the circle, so let's put this as an exercise, take just the circle x squared plus y squared equals 1, or the sphere x squared plus y squared, that square is 1. How many points are the finite field? And already that question you will see is non-trivial and interesting. And maybe that's a good exercise. Forgot to put it on the... But for a difficult, complicated variety, you have not much chance to find these numbers. But undeterred, we define further congruence zeta function, or sometimes called Hasse-Weil zeta function. So it is the generating series of these numbers, but you do the exponential. Now it was a k. You count these numbers and make them in a series. So this is a priori a power series in T with rational coefficients, because there is an exponentiation involved, so, and these are integers, but already non-trivial to say that indeed this is an integral. The coefficient turns out to be integral. It's a power series, integral power series. Not so difficult to prove, but we're not. And this is encoding our enumerative problem. So far, it's not different from many other problems where you form a generating series. Then you usually go and look at, is it D finite? What? In fact, this power series is rational. So this is one of the most surprising things, but let me say for an example, so if nk is p nk, so for x is the affine space of dimension n. So if there are no equations at all, you just count all the points, the number of points in the field of size p to the power k is just p to the power nk. And then you're dealing with the following series p nk p p. And this is just p to the k t minus logarithm 1 minus t, and then e to the power of that. Next. You have this series which is basically logarithm, but it is minus log 1 minus. Then you replace t by this variable. So this is this. Huh? Is it? N. And so for Pn, x is Pn. Well, the projective space is made up of a point, is stratified by affine spaces. So you find just by, because the numbers are additive and the exponential becomes multiplicative, so you get that the zeta function for Pn is just 1 over t 1 minus t Pn. Okay, this was easy, and there must be a way to move this thing. Some more blackboard here too. So this is the zeta function of P, and you see indeed it's a rational variety, and any variety which can be decomposed into affine pieces, like the Grassmannian, you will find a rational function. If x is an elliptic curve, people have looked in detail in examples, and you find that the zeta function of such an elliptic curve takes the form 1 minus AP t plus pt squared dividing 1 minus t 1 minus pt. And what one can also see that if we factorize this polynomial, so this polynomial is with coefficients, integer coefficients. And as such, this degree 2 polynomial is irreducible, but you might factor it in over the complex numbers, and you might write it alpha t. So beta is alpha. The product of the roots of alpha and beta is p. So if you know alpha, you know beta. And what one observes in examples, that the size of these roots are the same. And then, of course, the size must be the square root of p. And then this coefficient AP will be the sum of alpha and beta. So this statement is equivalent, in fact, to saying that the size of AP is smaller than t, 2 times the square root of p. So if you now go to general curve, so x is projective to smooth curve over fp, then examples show that it is always of this form, where p of 1 of t, here we got this polynomial of degree 2, but now this polynomial becomes 1 plus t to the power g, t to the power 2g, where g is the genus of the curve. And it is still in dt, of course, and you can factor it, and one find again experimentally that the size of these are all square root of p. So this is called the Riemann hypothesis, was called. Let me remark one thing, that for an elliptic curve, this formula with the zeta function implies the following, that the number of curves, so this is a n1, so the biggest lesson from this statement here is that there is one thing to determine, the AP. Knowing AP, well, this allows you to find out alpha and beta. And then it turns out by small calculation that the number of points of the elliptic curve over the extension field can be still expressed in alpha and beta in this way. So N1 determines the higher n case. This is very remarkable. In general, it's just finitely many of these numbers determine all the other numbers. So now I need a contribution of the University of Raleigh to our yeah. That is too much sophistication. But it's good that I will use it afterwards. Yeah, it doesn't run away. Yeah. Oh, this is the historical account of this. But let me put in some little history here. because it's interesting. So, Gauss, it turned out, had a mathematical diary, which he kept when he was young. And the last entry of that diary is in 1814. And there he looks at the following equation. And he gives a formula for the number of solutions. So he computes mod pi, where pi is a prime in Zi, in the Gaussian integers. Look at this equation. Well, this is in fact the lemniscate. You know that Gauss invented everything about elliptic functions and attached to the lemniscate. He considered the lemniscate as the next case after the circle. We have the circle, which is this equation, and then you have this one. And he discovered that that curve is what we now call complex multiplication by this ring, where the Gaussian integers come in. And he gives a formula for the number of solutions for this equation. Now, this is, of course, very remarkable because before Gauss, there was not a single person in the world who would mind or would have any interest in this. And in fact, for more than 100 years, apparently no one was interested until 1921, the mathematician Herglot, which some of you may know more as an applied mathematician. He worked on wave equations and applied mathematics and green functions. And he gave a proof. I must say that the Wikipedia page is wrong on this point because it does not mention Herglot. Some other pattern. Yeah. I think they refer to Chaula in 41. But the first sentence of Chaula says that the proof is in the... So, he was professor in Leipzig. So, in the same year, you have Emil Artin, famous algebraicist, writes his PhD thesis under the direction of Herglot, which is strange because he's not an algebraicist. He's not stemming from Frobenius or whatever. But this is one of the mysteries in the history of mathematics, how this person... But in that case, of course, mathematics was a unity, and everyone knew about everything. So, probably. Emil Artin is an interesting person because he also was a year here in Vienna. He studied here before going to Herglot because that was more exciting. And so he studied what is now called hyperelliptic curves. Hyperelliptic curves, and they saw it as it, or he considered it, it was generally considered it, as a theory about quadratic extensions, fields, over the function field fp of x. So you have a square root. And so it's very much like the rationals, and you have quadratic extension of degree D, 2. And here, of course, a lot was known and it was studied in great detail, the quadratic number fields. And they looked at this thing. And here one has the zeta functions for number fields and the Riemann hypothesis. So Artin in his thesis looks at this case and looks at the analogues of the Riemann hypothesis for this case. Now he didn't use that function, which is now called Artin-Hasse-Weil, but he looked at something which is equivalent. So it's basically that series where you substitute for t is 1 over p to the power s. Small difference. They were counting ideals. They were not counting points. They were counting ideals in the ring of integers of these things. Like 1 over n to the power s is a sum over the ideals of the ring Z. The Riemann zeta function interpreted in that way. And it was Emil Artin in his thesis who made these observations. And this was called the Riemann hypothesis. So in his paper of his thesis, you find about 50 examples worked out, and he observed all these properties, and but could not prove this Riemann hypothesis. And then Hasse famous proof for the Riemann hypothesis for elliptic curves. That was the only case they could do, but very much they were after proving this in the general case, and they did not succeed. And then André Wij published a proof but he didn't have a proof. It took 10 more years to develop the algebraic geometry over finite fields and formulate things which are known, in particular Castelnuovo's inequality for surfaces, which was known for over the complex numbers, but certainly not over FP. So, one must understand at that time that André Wij wrote this paper, he was imprisoned in France. So, but of course the German school, Hasse, Witt, Goering, this school, they were working hard on this problem on the Riemann hypothesis. And they knew this proof, more or less. They didn't care to write it down because they couldn't solve the final detail. So they were rather pissed off by it. And in 1994, so that's interesting, you get the wire conjectures. So in the German school, it is all about curves and analog with the field extensions. And André Wij asked Hasse in a letter, did you ever look at higher dimensional varieties? And Hasse answers, no, he had no interest in that. So one must say that the idea that this problem of counting points and putting it in this series is definitely due to André Wij. So what did he conjecture? That this function is a rational function. Rather, it's a power series expansion of a rational function. And if x is smooth projective, it factors in a specific way where the pi are polynomials, and more spectacularly, he claimed that the proof of this formula would most naturally follow from a cohomology theory, now called Weil cohomology, which would say that this formula can be understood as in terms of a Lefschetz fixed point theorem. So you have a Frobenius map. If you have a point, you just raise all coordinates to the pth power. This gives a map of the solutions to itself. And then the fixed points of the Frobenius map is just those points of the variety for xi is equal to xi to the power p. So they are the elements in the finite field Fp. And you have the fixed point of the square of the Frobenius is this, etc. So you have one transformation of the space or the set of points, and then you have the fixed points under the Frobenius. And now, if you have a similar situation in the topological space, you look at the action of that map on the cohomology, you would get a map Fi from the ith cohomology of x to itself. And then you would take the characteristic polynomial, which then would be, of course, a polynomial with integer coefficients. And he claims, or he asks whether one can have that we have an equality. So if you count points of a map of a topological space, you would have such a relation between the fixed points and the action on the cohomology. And André Weil suggests the same should hold for varieties over a finite field. Only the point is that we are over a field Fp, and this should be a vector space of characteristic 0. Well, maybe the rest of the history is known. Dwark was a student of Emile Artin, and Tate, who was married to his daughter. This Dwark proved the rationality in general. And to the chagrin and surprise of Serre and Grodny, he didn't use any cohomology at all. There is a nice letter of Serre to Grothendieck where he expressed the surprise about Borg's proof. And so it's a rational function, but to show that it factors in such a way that there is such a cohomology theory, it's a L-adic cohomology or crystalline cohomology, that is the work of a generation of mathematicians, which culminates then in the Leans proofs, the Riemann hypothesis in general, saying that the rods, the pi of t, can be factored in such a way that the size of these is pi over 2. So these groups are étale cohomology or crystalline cohomology. These cohomology theories are not easy to construct. Many details. You can devote your whole life in working out the details. And I consider it more as an invitation to think about it further and find easy ways to compute the polynomial pi using some sort of cohomology. And I want to report that that differential equations can help you, at least conjecturally. And so let me remind you once more of what I told in the first lecture, that elliptic curve. So we have that a function looks like this. And now the only interesting information is this AP. And I mentioned to you that Hasse was the first to show this number is always smaller than 2 square root of p. But Hasse was, of course, interested in anything related to AP. When is it 0? This is what now called the Hasse polynomial, with this trace 0. So this is the trace of Frobenius. This is characteristic polynomial. This is the trace of Frobenius on the first homology. Hasse had, of course, some group which plays the role of H1A of the étale cohomology, but he used the Jacobian curve. But it is the trace of Frobenius, this is the AP. And I mentioned to you that there was this calculation of Doering for the Legendre elliptic curve. So this is for ET. This was just E. But at least mod P. Oh. And so what you see here, and what was sensed by Dwork, that there is more to this story, namely, if you have a family, then these numbers or the zeta function seems to be related to the periods of your variety and the way they change the periods. The periods is if the variety depends on t, is a period function. It's an interesting function, and that function determines for all the parameters t the AP. So this is the AP ET. And it depends also on T. And the work found a way, if you factor that polynomial in the p-adic, as in the ring with coefficients, p-adic numbers, and there is in the case there is a root of this polynomial which is a p-adic unit, then he gives a formula for u. See, this is the unit root formula. This same polynomial. Before it was alpha and beta. Factorization of that linear polynomial in two factors. Formula for ut in terms of phi, the period I don't know if Masha is going to tell about the unit root formula, or maybe it was already mentioned. Exercise. Excellent. Dwork talked on it in 1962 in the ICM. I think it was a spectacular result. The periods determine the Euler factor. Now, and this thing itself is determined by a differential equation. So what I want to do is generalize this formula so that it works for higher dimensional varieties and gives you a way of calculating the number of points using only the differential equation satisfied by its periods. So this sounds incredible and crazy. It is intended to sound like that. And to be honest, we cannot prove much. We have an enormous number of numerical evidence, p-adic numerical evidence. And I want to tell you about that now. So somehow this, okay. So this is paragraph 2. Okay, so I forgot the numbering, but I will say a few words about Calabi-Yau manifolds. Because they form a nice generalization of the case of elliptic curves. So we say x in some projective space, smooth variety. They will always assume the variety is defined over Q, or even have defined by equations with coefficients in Z, so that I will later be able to do reduction mod P. But smooth of dimension D, and it's called Calabi-Yau. Variety, if two conditions are satisfied, functions on X, the structure sheaf, is the same as the sheaf of holomorphic D-forms. Another way of saying is that there exists a D-form, omega, which is a global section of this, which, by the way, is the Hodge group This is a global defined D-form on X with no zeros. It's never zero. No, D-form is a function times dx, dy, up to dxn. So you can have the divisor, and it should be, have no divisor. So this is the triviality of the canonical bundle. That's the first condition. And then the second condition is that, just to simplify matters, and one usually requires the chief OX have no cohomology where I is not 0 or D. The D cohomology is one-dimensional, the zeroth cohomology is also one-dimensional, so these groups are non-zero, but you require all others to be 0. So if D is one one manifold, X is elliptic curve. D is 2, so these are very well-known curves which even appear in Greek mathematics, antiquity, elliptic curves appearing. And then for these two, we have the theory of K3 surfaces. And for DS3, you have the Calabi-Yau, well, threefolds. There is no such a clear-cut description of them because it is a complete zoo. So this is where current algebraic geometry has not found a classification into types. The number of topological distinct types goes in the zillions. And it's unknown exactly what topology can occur. So we're entering terra incognita, or it is an unstructured zoo at the moment. But we have nice examples. So the Hodge diamond of the Calabi-Yau threefold, the interesting group is H3, such a thing, and it will have Hodge numbers H3, 0 plus H2, 1 plus H1, 2 plus H0, 3. And by the first condition, so this has dimension 1. This is its complex conjugate, this is dimension also 1. And then you have the Hodge number H21. H21 is the same, is isomorphic to H1 of omega 2. And this, because the three forms are trivial, is the same as H1 of the tangent sheaf. So this is the space of infinitesimal deformations. So this H3 will have Hodge numbers 1, tau, tau, 1, and the Hodge numbers, and tau is the number of parameters. In the elliptic curve, the H1 will have two Hodge numbers, and both are 1, 1. It also varies in a one-dimensional family, the modulus of the elliptic curve. Calabi-Yau threefolds have also moduli, and the number of moduli is this Hodge number. And the most interesting cases to look at first is where the number of moduli is 0. There are examples for those. But if you have something which depends on 0 parameters, there is no differential equation in sight. So I look at the case where tau is 1. look at cases. So, H3 will have Hodge numbers 1, 1, 1, 1. So it's a four-dimensional space. For the elliptic curve, the H1 is two-dimensional. Now we get something four-dimensional. And the interest in such, so in if you have such a variety over Fp, then the zeta function will have the following form. For the elliptic curve, there were P0 and P2, so there was 1 minus t, 1 minus p cubed t. For the elliptic curve, there was in the denominator 1 minus t and 1 minus pt, and there was on top, there was 1 minus alpha pt plus p times t squared. Now, we have also unknowns here, but what I am after is this P3. So this is the P3 will be sort of the characteristic polynomial of Frobenius on the third P times the Frobenius F3. So this is a polynomial of degree 4 now. There will be a P. And then by symmetry, there is P. No. So it is a polynomial which has now two coefficients to be determined. So this is the trace of Frobenius and the trace of wedge 2 of Frobenius. D determine P3. So this is everything which is dictated by the third cohomology. Now there are also contributions to H here, but they usually are very simple. In many examples, they are of the form 1 minus pt, 1 minus p squared t. Not always, there might be powers here. But this is simple, and the mysterious part is P3. And I will propose a formula for this determinant in terms of the periods of our Calabi-Yau manifold. So let me give examples of such Calabi-Yau manifolds. And if tau is 1, then vary in one parameter families. So we have many examples where we have pencils. So parameterized by P1. Families depending on one parameter which runs in a projective line. Pencils. Example is x1 fifth, 2 fifth, 5 psi. So this is x, it depends on parameter psi here in this equation. And this lies in the projective 4 space. And this equation is called, this is called Dwork pencil. But Dwork did not consider it. but he considered it with fours and the product of four variables, with sum of third powers and the product of three variables. So these are cases elliptic curve, K3 surface. This is the case of Calabi-Yau threefolds. And this became very famous because the cohomology is big, but there is a four-dimensional piece, which is the cohomology of a quotient of this variety. And you get a Picard-Fuchs equation, which is the following. Where t is now 1 over 5 psi to the power 5. Just a slight parameterization of psi and t. For t is 0, we get a differential operator with 4 exponents 0. So the Riemann symbol of this one looks as follows. Hypergeometric, but with a coefficient, so the singularity is moved. Exponents are now like this. You see, the exponents are 0, 1, 2, and an extra 1. Here we have a Jordan block of size 4, maximal Jordan block, and here there is a Jordan block of size 2. Here the monodrome is semi-simple. This is a beautiful equation, and it was used by Candelas, Ossa, Green, Parks, in their famous work in 1991, which used this differential equation to determine the number of rational curves of degree d on a quintic in P5, using this differential equation. So, from that time, Calabi-Yau threefolds are in center of interest, not only in mathematics, but also in theoretical physics. The formula I'm going to write down for the zeta function, or the factor of the zeta function, in terms of the periods, is in fact used by physicists. So this is the first one in a series of examples. This is called number 1. It's the first nice pencil. And we compiled a list, and on 34 we have the following period function. Very beautiful one. P factorial, Q factorial, R factorial, S factorial, T factorial, squared, P plus Q plus R is N. This series phi satisfies a fourth order differential equation, which is too complicated to write down, but I can write down the Riemann symbol. Here are the Jordan blocks. At 0, there is a maximal Jordan block. Here are Jordan blocks of size 2, size 2, size 2. And here at infinity, there are 2 Jordan blocks of size 2. But this is a period of a specific Calabi-Yau threefold, which is not going to describe, but and there is a complicated differential equation you can look up in the database we made for such operators. And this is just one case in a list of growing list of examples. And now I give you the formula for the factor of the zeta function, or this polynomial P3. So what we do, we have a so-called Frobenius basis. Solutions normalized in a specific way. So the first period is a power series, which in fact has integral coefficients. So this is the holomorphic period. In this case, the holomorphic period here is the famous 5n factorial n factorial to the fifth t to the n. That's a holomorphic solution to this equation. So, and then there is a logarithmic solution and there is a log square solution. T. And then there is log t squared with a coefficient of half. And then normalize it this way. And then there are here other log terms, and then there are some series which belong power series with rational coefficients which starts with t. This fixes a precise set of solutions to the differential equation, and these solutions now determine the polynomial P3 in the following way, apparently. So we write I'm running out of time, so I only give the. So what we write down is the fundamental solution of the differential equation. So this is a 4 cross 4 matrix. Well, but the entries are power series in T, and there are also logarithms. Now, we take this. And we put the logarithm terms, ignore, put them to 0. For no time in saying why this makes sense, but this is now a 4 cross 4 matrix with entries power series in T, formal series in T. And now I write another series so this is another 4 cross 4 and now F0 is a fixed matrix, but so we fixed now a prime is a prime, and a prime is a prime. And now we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime, but so we fix now a prime is a prime You have here, use the prime number here. So we take the, this is the fundamental solution. This is the twisted fundamental solution. And I sandwich it between a matrix. So this is not correct. So we write here QP maybe. So this is a matrix with entries in ZP. And the specific form of the matrix can be given not only in the 4×4 case I give here, but in the general case. And that is the following: lambda times gamma P. Lambda is a diagonal matrix, powers of P. So in the Calabi-Yau case, you go to P to the cubed, but in general you could go further, and this is product periodic gamma function. Epsilon is the nilpotent matrix appearing in the first part of the lecture, the maximal Jordan block. So this is an infinitesimal element. So this indeed gives derivatives of the gamma, periodic gamma function. And lambda I are the Chern roots of the mirror manifold. Whatever it is, the result for in the case V is 3, in the Calabi-Yau threefold case, the matrix F0 looks as follows: 1, 0, 0, 0, P, 0, 0, P squared, 0, P cubed. And then zeros here, and here is one non-vanishing entry, and this non-vanishing entry is a rational number times the periodic value of the zeta function at 3. This can be expressed as a third derivative of the periodic gamma function. So, of course, this is not motivated at all at this stage, but yeah. This conjunction. It is true in the hypergeometric case, because there we know it. Probably provable in the rigid case, but this case here is of course very far from rigid. Not a rigid local system, very special, but the method works, and it works in hundreds of examples. So what you then do is that the P3 of the variety of x at a certain point t0 is the determinant 1 minus this Frobenius matrix F evaluated at the Teichmüller lift. So parameter lifts may be in FP, but in order to get something in characteristic 0, you have to take the Teichmüller lift, and you can substitute it in this matrix, because modulo P, this matrix is a very nice expansion. Modulo P squared, modulo P cubed. So, and in this way you can compute this Euler factor this factor of the zeta function, from the differential equation alone. To be honest, there is maybe a sign here. So there is per p, there is a choice of a sign. And it means that you find the L function up to a twist. And this is the twist we saw in the exercise class last time, because we had the two singularities, and the two curves were not isomorphic, only over complex numbers. This introduces the sign. But these are so many details I cannot explain. This would require 2 other lectures. But maybe this gives an incentive to look further. I claim this is just the top of the iceberg. I mean, we made very special assumptions about the differential equation, having a point of maximal unipolar monodromy, but there should be something more general. I claim it will be easier. The more exponents are non-zero, the easier it becomes. This is sort of the irreducible mess, having all the eigenvalues equal, is the most degenerate case. But there we get a nice answer, which I think is remarkable. You can use this, it is used to locate parameters, something with black holes. This is used as calculations. So I must say this is joint work with Candelas and De La Osa and myself. So this is what we're working at. And Nutzai is also using this method to show that the cohomology of certain, the L function of certain Calabi-Yau threefolds corresponds to Siegel paramodular forms. We can identify the L functions and identify it with known L functions. So this is